Good evening, everybody. Happy Thursday. I am just getting some stuff set up here still. Um, Something interesting is happening on Blackboard in a sort of a dumb way that it I can't get the exam because it's trying to make me go into honor lock to be able to open the exam. So I'm trying to figure out how to not do that. And I assume that also means that when you all try to go review the answers, it's going to try to make you use honor lock as well. So let me see if I can disable this somehow. Let's see if this does it. Hey, Alyssa. Hey, Maria. Hey, Daisy. Daisy, I got your questions from Discord, so we will definitely go through those. Let me see if I can get this. Okay, so I got honor lock turned off, but now it's telling me that I cannot open it because the due date is passed. So this is fun. So anyway, everybody has taken exam 2 that is supposed to. So I think that means that I can make this available. And you should be able to review it. I want you to be able to see your answers and everything. And I thought we'd go over it today. That seems not to be working, but let's see if I can get it to work. All right, well, I can maybe, seems like it's maybe working. Hey, Jennifer. Yes, I got your questions as well. So we'll start with that while we see if this works. All right, so first question, is NH3 a weak acid? So this is it's a good question because it's not obvious. So the answer is yes. NH3 is a weak acid. But how would you know that? NH3 is a weak acid and a weak base. It's both. We usually refer to it more as a weak base, and here's why. So remember that acid and base, those labels, are roles in a reaction. So there could be a reaction where NH3 gives up its hydrogen. In that case, it's acting as an acid. But more commonly, NH3 takes a hydrogen, which makes it a base. The thing that's a little bit confusing about this is most of the other bases that we've seen are hydroxide bases. So sodium hydroxide, calcium hydroxide, stuff like that. We haven't really dealt with these. So why is this a base if it's not making hydroxide in solution? And the answer is because it kind of is making hydroxide in solution. So when you put ammonia in water, so ammonia is actually a gas at standard, room temperature and pressure, and water is a liquid. When you put those together, the ammonia dissolves in the water. They're both hydrogen bonding, but we also get an acid-base reaction. So we get a solution of ammonium and hydroxide. So in this case, in this reaction, and I think did we look at this one? No, we didn't look at this one yet. So in this particular reaction, what's happening, if again we track the hydrogens, the hydrogen is moving from water to ammonia. So that makes water the acid, getting rid of its hydrogen, donating its hydrogen, and ammonia the base by accepting that H plus. So when you have a solution of ammonia, like Windex or something, actually mostly what it is a solution of ammonium hydroxide. But because of this equilibrium, it's also producing some ammonia, which is why it is kind of smelly and can be a problem that way. So ammonium hydroxide is in water is actually increasing the amount of hydroxide. Right? By having ammonium hydroxide, you're increasing the amount of hydroxide in solution. So that's why ammonia is acting as a base, because in water, it is creating hydroxide. No, there isn't a Mastering Chemistry acid base one yet. It's going to come up for next week, so we're a little ahead of schedule on that. I think this was just a general question. There is a practice sheet in acid bases that we're going to look at in a second. Jennifer asked about that. All right, so the next question is about calculating pH and OH. Yes, you should calculate. You should be able to calculate those given the hydronium ion concentration. And it's really as simple as plugging it into your calculator. Oh, hello. So if you have the hydronium ion concentration, let's say it's we'll just make up some random number, 2.73 times 10 to the minus 4 molar. Okay. Whoops. All right, sorry, I kept knocked over my stuff again. Just a second. All right. It's not centered well, but I think it's working. Okay, that looks better. There's a little corner, but that's all right. So to answer the questions that have just come up, please, or there is. So where's this question from? I'm not sure. I got it on Discord from somebody, so it might just have just been a general question, like, is ammonia a weak acid or weak base? Do we have to know which ones are weak bases and acids? So if you check on Blackboard, there is a list, and it says that you should be able to name a few examples of strong, weak acids and bases. You don't have to know every one. You don't have to know the whole list of everything, but you should know that there is a difference and which one, and just some examples of which ones are which. All right, so we're so back where I was here. All right, so here's a hydronium ion concentration, and we want to know the pH. So to do that, we need to know that the pH is calculated by taking the negative log of the hydronium ion concentration. So we need to put that number into our calculator, take the log of it, and then switch the sign. So let's see if I can do that on screen here so you can see what that looks like. Okay, you see the calculator there? It should be there. So if you just have a regular 4-function calculator like this, you can't do that. You need to have a scientific calculator that can do logs. So I'm on Windows here, so I think I can switch it. Yeah, so I can switch it to a scientific calculator, and now I've got my log function down here. So I can take that number, which I know the calculator is hiding it right now. But it was 2.73 times 10 to the minus 4, so 2.73. And then most calculators have some way of easily doing scientific notation, like especially graphing calculators. This one looks like maybe it doesn't, but we can just go times. No, I don't want to do that. All right, let's try this again. Okay, we'll just do it manually. So 0.000273, that's 2.73 times 10 to the minus 4, right? So then we'll take the log of that, and we get minus 3.56. So then the negative log, we switch the sign, so the pH is 3.56. And so that's our pH. And that's how we calculate the pH from the hydronium ion concentration. If we want to know the pOH, well, we remember from last time that the pH plus the pOH always equals 14. So as long as you know one, you can always get the other one pretty easily by just subtracting it from 14. So 14 minus 3.56 equals, what is that, 10.44? Yeah. And so now we have the pOH. Okay, and then looking back at buffers, so the definition of a buffer is just a solution that can maintain pH when more acid or base is added. So it can hold an appropriate pH. And there is a limit on that. Eventually, you could add enough acid or base to make the to change the pH, but the idea is that within a range, the buffer can hold that pH. So to identify buffers, we didn't really talk about that, but buffers are always made from weak acids and their conjugate base. So just as an example, if you had something like carbonic acid, which we talked about, and that was mixed with, let's say, sodium bicarbonate, we can recognize that bicarbonate, HCO3 minus, is the conjugate base of carbonic acid, and so a system of these two together will likely act as a buffer. Another example might be acetic acid and sodium acetate. All right, so the acid and then the conjugate base. All right. Any questions about those ideas? Okay, so interesting. Can you make a buffer from H3O plus and H2O? I don't think so, because that's a good question. H3O plus I would consider to be a strong acid, so because that's like that source of acidity. So I don't think that's right. H2O and OH minus, I don't think that has buffering capability. Because yes, H2O is a weak acid, but because of, if you imagine like what would happen if you add more OH, there's nothing really to like absorb that OH. So I don't think those are buffer system. I don't think those would be buffer systems. But either way, I don't, that wouldn't come up with those specifically. All right, so here's some of the acid-base practice that is on Blackboard. And it's kind of split into a couple parts. One, can you predict products? And when we talked about chemical reactions a couple chapters ago, we didn't really talk much about how to predict products of reactions, because it's a involved topic and it's not always easy to do. But in this case, when we're specifically talking about acids and bases, it is actually fairly easy to predict the products, because we know that all that's going to happen is the acids are going to lose their hydrogen and the base is going to accept their hydrogen. Where that can get a little bit tricky is deciding first, what are the specific acidic and basic species? And it may not be the entire thing, the entire formula, it may be a piece of it. And so we'll look at that. And then also, how do we know how many hydrogens are going to transfer? And we'll talk about that as well. So this is a good example of what we were going to be talking about anyway. So this first one, we've got nitric acid and barium hydroxide. So the first challenge here is to just identify this as an acid-base reaction. How do we know that these are going to react in that specific way? And the key is recognizing these molecules that always act as acids, that act as acids so often that they actually have the word acid in their name. So we talked about how acid is a role, not an identity, that, you know, water can be an acid if it gives up a hydrogen, but there are some molecules that so reliably act as acids that they're just called acids, and those are always, their formulas always start with hydrogen. So this would be nitric acid, phosphoric acid, hydrofluoric acid. So seeing those can give you a pretty good clue that this is going to be an acid-base reaction. So if that's the case, then we know that this, whatever this is here, I'll make this a little bit bigger. We can see it better. Whatever that is, it's going to be losing its hydrogen. So once we identify that something is an acid, we know it's going to lose hydrogen. And so then the other decision we have to make then is, what's the base? What's getting the hydrogens? Is it barium hydroxide overall? Are we going to make HBaOH2? And the answer to that is no. So with charged particles like hydroxide ions, we can't just add ions to a solution. They always have to have a counter ion. I'm sorry, we can't just add an ion. So we can't just, you can't have a bottle of hydroxide. It has to have a cation to balance its charge. So it could be sodium hydroxide, it could be barium hydroxide, calcium hydroxide, lithium hydroxide, but it's got to have some other ion there balancing it out. But remember what we talked about with solutions in the last chapter. When an ionic substance, an ionic compound dissolves in water, it's no longer together. The ions break apart and get surrounded by their water solvation spheres. So when you put barium hydroxide in water, you expect that barium to get surrounded by water molecules, and you would expect the hydroxide molecules, or the hydroxide ions, to also get surrounded by water molecules. So really, when we say aqueous barium hydroxide, what we're really saying here is that there are barium ions and there are hydroxide ions in that solution. That's what that really means. So that means that when we do this acid-base reaction, it's really the hydroxide that's acting as a base. We know that hydroxide is a nice strong base that can take hydrogen and make water. So whenever we see hydroxide in an acid-base reaction, we expect that the hydroxide is going to be the thing that grabs that hydrogen. And then that makes one of our products water. Just plain old liquid water. So you got OH, you got H, you get water. All right, so then what's the other product of the reaction? Well, the other product is just the other ions. So if the H and the OH get together to make water, what's left? Well, what's left is barium and nitrate. So the final compound then in this reaction is going to be aqueous barium nitrate. Okay. So we kind of switched partners here. The OH and the H got together and made water. The barium and the nitrate got together and made barium nitrate. And then we have to also remember back many, many chapters now to recognize that in an ionic compound, the charges of the ions have to balance. So when we make barium nitrate, it can't just be BaNO3. It has to be BaNO3 2, because we know nitrate is -1 and barium is +2. So all this stuff keeps coming back from the stuff we did before. We have to know that barium is a +2 ion. We have to know that nitrate is a -1 ion so that we can get the correct formula. Now that we've got the correct formula, we can do the final step and actually balance this. So that means that we're going to be looking at the nitrates. So there's 1 on the left and 2 on the right. So we need a 2 over there. And then I think that does it. So we could go through the whole balancing thing, but I'm pretty sure that's right. Yes, definitely I would say OH gets the H. The only time that that gets tricky is if the base is not a hydroxide base, if it's ammonia or something, and then the ammonia is getting the hydrogen. But whatever is not the acid is getting the hydrogen, and if it's in an ionic compound like this, it's definitely going to be the OH that gets it. Okay, so that idea holds for the rest of these problems also. The thing that changes here is that in this case, this acid has phosphoric acid has 3 hydrogens, whereas the calcium, so like when we talk about losing a hydrogen, how do we know, do we lose all of the hydrogens, or do we lose some of the hydrogens, or do we lose one of the hydrogens? And sometimes the answer is we don't really know. And that, I mean, that's a problem because you have to kind of look up these constants to actually see if it works or not in many cases. But when we can say that we can pretty reliably know it is when we know that one of them is strong. So if we know that if we know that hydroxide, for example, is a strong base, then we can expect that hydroxide is going to take all the hydrogens. So when we write the products for this reaction, once again, the hydroxide takes the hydrogen and makes water. And the other product then is not calcium dihydrogen phosphate. It's just going to be calcium phosphate. So we're going to assume that all 3 of those hydrogens go over to make waters. And that is not a like all of chemistry always assumption, but that's going to work well in our class. You can assume that unless the problem or whatever specifically says that's not the case, you can assume that all of those hydrogens are going to come over. So that means the other product is calcium and phosphate without any hydrogen at all. And that looks like Ca3PO4 2. All right, so then once again, we have to balance it. 3 calciums, so we want 3 calciums here. 2 phosphates, so we want 2 phosphates there. Oh, I'm sorry, this one up here was not balanced properly. There should be 2 waters, and then there should be 3 waters here. No, sorry. 6 waters, right? 6 waters. So the way that I'm trying to figure that out, just so I don't, you could do it the right way and write out all the atoms. But as a shortcut, I'm keeping the phosphate together and saying if there's 2 phosphates here, there's got to be 2 here. And then I know that the hydrogens are going to become waters and the hydroxides are going to become waters. So I have to have as many waters as I have hydrogens and hydroxides. because those don't get broken up here. So I need 6 waters there. Okay, I'll leave the last one for you. I think you can figure it out. These issues that we talked about with multiple hydrogens do not come up in that one. So it's just a matter of making the water and then making the correct compound out of the other ions. All right, let's talk about some of these. So we want to we want to take the data in the table here to talk about if we can tell that something is an acid or a base. Excuse me. So first, gives up an H plus. Well, okay, so right there, we don't even have to know the rest of this, right? If something gives up an H plus, it is definitely an acid. And then so that substance, if it gives up the H plus to form HSO4 minus, it must be H2SO4. If it has a pH of 10, that's a base, right? But we don't know any name or formula there, so we can't fill that one out. If it has a hydrogen concentration of 2.3 times 10 to the minus 6, that's going to be an acid, right? Because that's if we have to take the negative log, but it's going to be below 7, so that's going to be a weak acid, very close to neutral. If it's got a conjugate base of Br, then Br minus, then that means that it's an acid, so it's going to be HBr. If it picks up a hydrogen to form HNO2, then it's NO2. So you can see how this kind of works. And then the idea here is to put those on a pH scale. So which ones are going to be more or less acidic? And this may be difficult to do. It may actually be somewhat impossible in a couple cases. The point isn't to get an absolute correct answer. The idea is, can you roughly get these in line? So if you haven't had a chance to try this yet, go ahead and do it, and let's come back and talk about it again on Tuesday, so that we can kind of see how it went. Because I don't want to just like give you all the answers to it if you haven't had a chance to look at it. But I'll go through it and I'll tell you some of those issues where some of them are maybe not as clear as they should be. And then for the last time, or for the last one here, it's some naming practice. Now, if you look at the whoa, what happened? Okay, if you look at the objectives on Blackboard, you don't have to know the names of all these different acids, but it can be good practice to see if you can name them. And we don't have these game cards. That must have come from a different class. I'm not sure what that's all about. But the idea with these, all of this is really much more difficult than you would see on a quiz or exam. The idea is to kind of test yourself, to look up answers, like with mastering chemistry, where you have to look stuff up and find data to make it work. You'll definitely start to see some patterns with naming the acids, and you can go back to the chapter where we talked about the rules for naming the acids if you have specific questions. Since you don't have these dies and these cards, I didn't this must have come from somebody else because I'm not sure what that is. So like for some of these, you're not going to be able to. Well, for this one, you can do it by just picking a bunch of different cations. Pick whatever you want. You don't have to do all of them. Just do some cations, and then for the acids, you can use these different ions and see if you can make acids from there and name them. And so you should be able to do most of these. You may have to look some stuff up to get some of the names right. This is just for practice. You don't have to turn this in. It's just in the activities folder, and just for practice if you want. So this week, there is not much due. The lab, the post lab for the why can't I think the the mixtures, the solutions lab that we did either just yesterday or last week is due this week, and that's it. So there will be a combined mastering chemistry assignment with acid base and the very beginnings of the organic chemistry stuff next week. So our next unit is talking about organic chemistry and structures, and there's not a lot of good questions in mastering chemistry with that because you have to use the drawing thing, and it's just, well, you saw when we did Lewis structures, it's just kind of tedious to try to figure out how to draw with all those with that stuff online. So the mastering chemistry assignment's going to be more on the acid base side, and the drawing structures we'll just do and have some practice. Oh, there's no assignment on Blackboard? Okay, I'll put one up there so that you can turn that in. Okay, so to answer Jennifer's question from above, what does it mean to determine the formula of conjugate acids and bases? So this is what kind of what we did on Tuesday and what you and I did together in lab on Wednesday, where if you're given some formula, can you come up with a formula for the conjugate acid and or the conjugate base for it? Right. So for example, here we go. So if I gave you something like HCO3 minus, that's a bicarbonate ion, I could ask you, what is the formula for its conjugate acid? And the formula for its conjugate acid is H2CO3. So whenever we want to find a conjugate acid, we add hydrogen ion. And if we want to find the conjugate base, we take it away. So if that's the conjugate acid, then the conjugate base is CO3 2 minus. So we take the hydrogen away. And that's the determining the formulas of conjugate acids and bases. Yep. All right, let's see if I got this thing to print properly. Okay, it looks like it did. All right, it might be a little weird. It might be formatted a little weird, but we'll see what we can do. So the exams are done. I have not graded all of the free responses yet. They came in some different forms, so I have to kind of put those together and do it. But I think I have removed all the security stuff on the exam now, so you should be able to go in and see your answers, which questions you got right, which questions you got wrong, and the correct answers. So I do want to go through it if we have time. Yeah, I think we'll be good. All right, so just some metric practice here. A kilogram is 1,000 grams. A meter is 1,000 millimeters. A centimeter is 10 millimeters. And 1 millimeter is 1 cc, or 1 cubic centimeter. All right, looking at some gas laws. What happens to the pressure when we have the following changes? So if there is a decrease in volume, then there is an increase in pressure. If some molecules of gas are removed under constant volume and temperature, then the pressure decreases. If the temperature is doubled under constant volume and constant number of moles, then we'll see an increase. If the volume and the temperature are both reduced by 1/2, so this is a little tricky, right? So the volume, we have to think of them separately. The volume being reduced is going to increase the pressure. The temperature being reduced is going to decrease the pressure. So overall, we would expect no change there. And then if a leak occurs and gas escapes, that's essentially the same as the second one here. So that would be the pressure decreases. Yeah, so this one I can't see well, but we can figure it out. A mixture of sodium chloride and water is a solution. If the particles, I can't see if that's can go or cannot go through the semipermeable membrane, then it is, if they can go through the semipermeable membrane, it's a solution. If they cannot, it's a colloid. If the if it can't be separated by filters or semipermeable membranes, um, then it's a solution. And I can't see that one again. So hopefully you can see that. I don't remember what it said. Oh wait, you know what? Maybe it's still up here. Hold on. Okay. So the third one was a homogeneous mixture in which suspended particles cannot pass through a semi-permeable membrane. That would be actually, if it's a homogeneous mixture, then it's got to be a colloid, right? Because if it were a suspension, even though it uses the word suspended, a suspension is not a homogeneous mixture. And then if it's a mixture whose particles can be separated by filters, that is a suspension. All right, to calculate this one, we have to find the molar mass of NO2. So we're going to say 14 for nitrogen and 16 for each oxygen, and then add those up and multiply by 3, since that's how many grams are in 1 mole, and here we have 3 moles. Chemical equation is balanced when the last one here, the number of atoms of each element is the same in the reactants and products. So it doesn't worry about the total number of ions or the total charge on each, or the charge on each atom. The sums of the coefficients don't have to be the same. The molecules don't have to be the same, but there has to be the same number of atoms on each side. All right, this one, same idea with NO2. We got to look up the mass of magnesium and the 2 chlorines to do that, and then add those up and get the mass. This one, again, the question is covered up, so let me read it to you. How many atoms of neon are present in 1.30 moles of neon? So we're going to set up a conversion here, 1.30 moles of neon. And then we want to go moles to atoms. And that's 6.02 times 10 to the 23rd atoms in a mole. So 1.3 times 6.02 times 10 to the 23rd is going to be this one, 7 point, no. Oh, I think the correct answer is covered up because none of those look right to me. Yeah, it should be 7.83 times 10 to the 23rd. Okay, if the reaction is exothermic, the energy level of the reactants is lower than that of the the energy level of the reactants is higher than that of the products. So you should have this kind of a shape if you've got an exothermic reaction where the reactants are at a higher energy and the products are at a lower energy. All right, grams to moles. Again, we have to calculate the molar mass of water. So 16 for oxygen plus 1.01 plus 1.01 is 18.01 grams per 1 mole. So if we have 75 grams, we want to cancel grams and get moles. So we're not multiplying by the molar mass. This is grams per 1 mole. So we put that one down here, per 1 mole, and we divide and get one of these. I don't remember which one, but you can do that division and figure it out. All right, 5.21 centimeters is going to be the same as 0.0521 meters. So we can do that conversion. Okay, and then one of these dose questions, which you can't see here. I think we might have done this question or a question very much like it in class, but it reads, a doctor's order is 125 milligrams of ampicillin. The liquid suspension on hand contains 250 milligrams per 5 milliliters. How many milliliters of the suspension are required? So for that one, because the numbers work out nicely, the order is 125 milligrams, and the suspension is 250 per 5 milliliters. So you might have just been able to figure out that you need half of the ratio there, of the dosage ratio, or the concentration. So you need 2.5 milliliters, 2.5 milliliters, half of what's given there. But if those numbers weren't as easy, or if you wanted to try to figure that out, you'd set that up as a conversion where you'd say 125 milligrams times a factor that relates milligrams and milliliters in a way that milligrams can cancel, and that's 250 milligrams per 5 milliliters, and so you'd get 2.5 milliliters. Okay, for this one, you've got the mass of the gold and then the water level. So the water level changes from 50 to 77, and that's the overall volume then of the gold. So the density is the mass of the gold, which is 521 grams, divided by the volume of the gold, which is the difference in these two volumes. So 27.0 mLs. And it comes out to 19.3, which is actually the real density of gold. Stop me, by the way, in the chat if you want to talk more about these. I'm kind of just going through quickly, but if you're not sure about one or you don't know why, just let me know. All right, for something to float in something else, it needs to be less dense. So balsa wood is the only one that has a low enough density to float in water. If we have a 4% starch solution and a 10% starch solution, and those are separated by a semi-permeable membrane, the starch can't get through the membrane because the starch particles are too big. That's a colloidal solution. So what happens is osmosis, where the water moves from the 4% solution to the 10% solution. All right, and then this one's talking about a polar solvent, water and hexane, and which solute is correctly described here. In this case, the ionic and polar solvents can dissolve in water. Non-polar solvents can dissolve in hexane, or solutes can dissolve in hexane. So the non-polar, or the polar and ionic solutes here that are listed are calcium chloride, and then I think there's one covered up here. I think it's a bicarbonate, if I remember that question correctly. Yeah, sodium bicarbonate, soluble in water. So sodium bicarbonate is soluble in water. The other ones are all mismatched. So for example, octane, C8H18, that is all nonpolar. So it cannot be soluble in water because we know carbon-carbon bonds and carbon-hydrogen bonds are nonpolar. All right, the OH bond in water is polar because of the electronegativity difference, the second one there. If something partially ionizes in solution, that is a weak electrolyte. If it fully ionizes in solution, it's a strong electrolyte. And if it does not ionize in solution at all, it is a non-electrolyte. It does have to do with conducting electricity, but a semiconductor is a different thing, so that's not applicable here. All right, the solvent in a solution can be solid, liquid, or gas. Hydrogen bonds are a major factor. Remember, they can only be a major factor if you have OH, NH, or FH bonds. So in of these examples, I know it's covered up here, but it should be DNA. We know that those hydrogen bonds help hold those nitrogen-hydrogen bonds help hold the two helices of the DNA together through those base pairs. Okay, if you put some sugar in iced tea and it remains at the bottom of the glass and is not dissolved, then that means the solution is saturated because no more sugar can get into that solution at that temperature. NH3 is the only one here that can form hydrogen bonds because of the NH bonds. These all have hydrogen in them, but you have to have OH, NH, or FH bonds to make hydrogen bonds. Isotonic, we talked about that, is 0.9% NaCl. A fast reaction rate means having a small activation energy in the for the reaction. And an enzyme lowers that activation energy, which makes it faster. All right, so here's our figure of these two reactions. The activation energy for reaction 1 is smaller than reaction 2. That's correct. Reaction 1 is exergonic, which is the energy version of exothermic. That is true. Reaction 2 occurs faster than reaction 1. That would be false. And the reason we know that's false is because reaction 2 has such a high activation energy. So much higher activation energy makes it slower. Okay, these are all covered up, but hydrogen bonding is not a factor in, what's the correct one there? In CH4. CH4 is nonpolar, no electronegativity differences. We're not seeing hydrogen bonds there. And so the definition of that and why that relates to the speed of the reaction, the activation energy is the energy needed to orient the molecules so they can react properly. The hot air inside the balloon is less dense. That's why the hot air balloon goes up. And remember that boiling points are correlated to intermolecular forces. So the higher boiling points are the stronger forces, and the lower boiling points are the weaker forces. So in this case, strongest would be water, then ethanol, and then ammonia. Okay, balancing equations, you can do that. This is one of those ones. I think we did this exact one in class. You can go back to the video or the notes, but you have to end up doubling the butane here so that the numbers work out, because otherwise you're trying to balance an odd number of oxygens with an even number of oxygens, and you can't get it to work. Okay, this question is also covered up, but it says, when an ionic compound dissolves in water, and the correct answer is that the negative ends of water molecules surround the positive ions. So the water molecules split into a polar kind of positive and negative side. And the positive side goes around the negative ions, and the negative side goes around the positive ions. All right, which would not increase the rate of a reaction? Diluting the reactants, right? Diluting the reactants would slow down, decrease that rate of reaction. Increasing the concentrations would speed it up. All right, what's not part of the kinetic molecular theory? That molecules of a gas are strongly attracted to each other. In fact, the theory says that gas molecules do not interact at all. That when they collide, they just bounce off each other with no energy transfer. So there's no attractions there. All right, so another one covered up. This is kind of annoying. Same intermolecular forces. The answer there is that ethanol and water contain the same hydrogen bonding forces. So CH3, CH2OH, and H2O. Another covered up one. Which state of matter has molecules close together but moving randomly? That's liquid. So solid has molecules close together, rigid in place. I mean, they're still vibrating, but they're not moving really randomly. And then gas has them far apart and moving randomly. All right, so then we've got this balancing question, and this one is tricky because there's a lot of weird stuff going on, and a lot of words that sound very similar. So you've got aqueous aluminum acetate with aqueous ammonium phosphate to form solid aluminum phosphate and aqueous ammonium acetate. So you really kind of have to go through each of those compounds, like, okay, what's aluminum acetate? Well, acetate is given. Acetate is C2H3O2 minus 1. So then we have to find a formula that pairs aluminum, which we know is a +3 ion, with acetate, which is a -3 ion. So that means we must need 3 acetates for the 1 aluminum. So that actually narrows down the whole question right there, because this first answer is the only one that works, because these two have the wrong formula for aluminum acetate, as do the last couple. All right, mass percent is solute divided by mass of solution, so 15 grams divided by the sum of all three of those together. And this one, again, covered up, but I'll read it. A solution is saturated in both nitrogen gas and sodium iodide. So it's got as much nitrogen as can go in and as much sodium iodide as can go in. When the solution is cooled to 25, which of the following is most likely to occur? So if it's cooled, then we have to think about how that affects gas solubility and solid solubility. And generally, gas solutes dissolve better at colder temperatures. That's called Henry's law. And solid solutes dissolve worse at low temperatures. So if we lower the temperature, we would expect the solid solute, the sodium iodide, to precipitate out, but we would expect the nitrogen to stay there. So if it's saturated in nitrogen and you drop the temperature, then it's actually not saturated in nitrogen anymore. Now you could actually put more nitrogen in if you wanted to at the colder temperature. Right, to calculate moles from molarity, we take that 750 milliliters and convert it to liters. So that would be 0.750 liters. And then times the concentration, which in this case is 5 moles per liter. And so I think that's 3.75 moles. For the solute to dissolve in solution, the solute-solvent forces must be greater than the solute-solute forces. So the interactions between the solute and the solvent have to be stronger. Otherwise, the solute and the solvent are just going to stay with their own molecules and they're not going to mix. So the mixing interactions have to be stronger than the non-mixing interactions. Okay. A liter of gas is in a sealed chamber containing a movable piston. If the piston moves, so the volume is compressed to 1/2 liter, what will happen to the pressure of the gas? So we've got a piston, and there's a liter there, and then it's compressed to 1/2 liter. So that means the pressure is going to go up. So it's going to be twice the original value because we compressed it by half. For the concentration here, we have to take that 10.7 grams of sodium iodide and then convert it to moles. So that would require knowing the molar mass of NaI, dividing 10.7 by that molar mass, and then dividing that number by the total solution, the 0.25 liters of solution. And you can see the answer when you go back into the exam. Okay, so on to some of the free response ones. We've got a temperature conversion here, and the equations are given to you there. So you just take the Fahrenheit temperature, plug it in there, solve for the Celsius temperature. And so then let's just do that. So that ends up being about 141 degrees C. Okay, aircraft cabins are pressurized to 562 torr. What is that in atmospheres? So 562 torr. We know that the conversion between torr and atmospheres is 760 torr per 1 atmosphere. So this is going to be 562 divided by 760, which is 0.74 atmospheres. Oh, yeah, of course, we've got this giant weird editor thing. What happens when the hypotonic solution is separated from a hypertonic solution? Well, we know that the water is going to move through from the hypertonic side to the hypotonic side until it is all of even concentration. Right. If we have some vitamin D, which is actually a mixture of a few different molecules, but it is insoluble in water, and it is soluble in benzene, which is then nonpolar, we can say that vitamin D is likely nonpolar, which is true. It is, actually. All right, for the equilibrium one, this one's covered up again, so let me get it. So we're looking at nitrogen and hydrogen becoming NH3. If you add more on the reactant side, then you would expect the equilibrium to shift to the right. So if you add, we talked about like thinking about buckets filled with water connected by a tube. If you add more on one side, it's going to push more over to the other side. So if you add more nitrogen on the reactant side, then you will push more over to the product side, the NH3. Okay, and then we've got the cell thing going on here. Oops, missed that one. A hypotonic solution with a blood cell inside means that there's going to be more dots inside the cell than outside if dots are the solute particles. And that means that water is going to go from the outside to the inside. And that's lysis or hemolysis if it's a blood cell. I don't see anything coming up through the chat. I'm assuming there's no questions. That's fine. You don't have to say anything, but I just want to make sure there aren't more questions. And to calculate molarity, again, we got to find the molar mass of this, then divide 12 by that molar mass to get moles, and then divide by 0.75. So we have to remember that molarity is moles of solute divided by liters of solution. So the denominator, the liters, the solution volume has to be in liters, so that's 0.750. The top of the fraction has to be in moles, so that's 12 divided by whatever the molar mass of NaNO3 is. And that's it. So if you have more questions about the exam, or I'll go through and grade the ones that you typed in, but if you think something else went wrong or you should have gotten more points for something, definitely let me know. In terms of lab next week, so there's no lab scheduled for next week or the week after. The week after is Thanksgiving. The idea is to have next week open as a makeup lab for people who have to come in and make up a lab. Now, if you missed the last two labs, you don't have to come in and make those up, because one of them, everything was canceled, and this past one, a lot of the stuff was, or a lot of people had to miss that also. So don't worry if you missed those. You can just complete the report. With this past one, you don't even really need the data. You can, well, I guess that's not true. I'll have to post the data for this one for you to finish that up. But we already have the one from 2 weeks ago. If you missed one of the earlier labs from earlier in the semester, let me know, and you can come on Wednesday. Now, this is all a little bit up in the air right now because of all of the closures, and like my local school district just closed everything for the rest of the year. So we may be, watch your email. We may be getting messages that we're not coming back on campus at all. We'll see what happens. But the plan is for next week to be for anybody who needs to make something up, and then nothing Thanksgiving week, and then we should have one more in-person lab after that. Whether it happens or not, we'll see. But I will let you know as soon as I know how that works. Until then, happy chemistrying. Let me know if you need anything. Be safe, and hopefully we'll get to see each other again. And yes, the pH values are always negative log. Right. All right. Good night, everybody. Thanks.